welcome to the 51st lecture in this series. Last time I had introduced this operation of antisymmetrization, where you start with any multilinear form and you end up getting an alternating form. And the definition, so I realized that there's a small correction one has to make. It's more of a typo. All along I have been writing -1 raised to sine sigma. What I meant was just sine sigma rather than -1 raised to sine sigma. So for instance here it should be sine sigma. And it unfortunately this I made this this correction should be made in various places. Let me just quickly go over sine sigma, and in fact even in the proposition where I say that here I need to just write sine sigma. Right, so now coming back to this, let's check. So we are in the process of checking that this definition actually gives an alternating form. That so I started writing something. Let me write it in a slightly different way. So this is what. So I started with any sigma naught, and then I did sigma naught of alt alpha. Then I get this sum. Now let's call this rather than putting it like this, let's say that note that as sigma varies over sk, sigma dot also varies over sk, i.e. this set, this sigma dot over all sigma in sk is actually equal to sk again, which is just another way of saying that. I mean, all I'm doing is I know that sk is a group. I'm multiplying every element of sk by on the right by some fixed element of sk. So naturally I get the whole group again. So now because of that, what I can do is I can write this. Let's look at this term here, an individual term. So alt alpha acting on V sigma dot 1 is equal to tau, the permutation tau times alt alpha acting on V1 Vk, where tau equals sigma multiplied by sigma naught, this permutation. So I can rewrite the whole sum in terms of this tau. Therefore the star equal to 1 over k factorial. Now the remark that I made here is that the values, the permutations over covered by tau is the full symmetric group as sigma varies over the symmetric group. So I can write it as tau in Sk, and then what I had here is -1 raised to sine sigma. Now here is an aside, this it's an easy consequence of the way the sign of a permutation is defined, that the sign of a product of two permutation is just the product of the signs, sine sigma, sine sigma naught. And this is quite straightforward, since the way we defined sign was you write sigma as a product of transpositions, then you count how many there are. The even number, the sign is +1, otherwise -1. Same thing here. So if you have a product decomposition of sigma, if you have a transposition decomposition of sigma and a transposition decomposition of sigma naught, you get a, since this is a product of two permutations, you can just multiply both these decompositions together, and from that it immediately follows that this, if both, for instance, if both are even, then the product will also have even number of permutations. If both are odd, the product will have again even number of permutations. If one of them is even, the other one is odd, the product will have odd, and so on. So one gets this essentially. So because of that, oops, again I'm resorting to this unfortunate thing about writing it like this, sine sigma, and here it is sine sigma, and then the only thing I've changed is, instead of, I'll write it as tau alt alpha V1 up to Vk Now notice that because of this comment that I made here, sine tau is the same as sine sigma times sine sigma naught. If I multiply both sides, the sign is either +1 or -1, so I can multiply by sine sigma naught on both sides, and I get sine tau times sine sigma naught equal to sine sigma. And I can put it here, and I am left with tau in Sk. This is tau sine tau sine sigma naught tau times alt alpha acting on V1 up to Vk. Right. So now I can write it as, actually I need not, okay, that's fine. So 1 over k factorial. So the point is I can get the sine sigma naught out. That is something which is independent of tau. So, and then tau in Sk sine tau, and then I just write it as alt alpha V tau 1 V tau k. where tau varies over all permutations. And this we know is the same as, so the 1 over k factorial, again I combine with this, and this is the same as alt alpha acting on V1 up to Vk. So essentially we started with sigma naught of alt alpha acting on V1 up to Vk, and we ended up with sine sigma naught alt alpha V1 up. So therefore this alt alpha is alternating. Now if alpha is already alternating, one would like to check that the value of right, where was I? Yeah, if alpha is already alternating, then I would like to check I end up with whatever I started with, and that is clear as well, simply because well, if alpha is already in what is this? Alpha is already in AKV, then alt alpha acting on V1 up to Vk is 1 over k factorial sigma in Sk sine sigma alpha V sigma 1 V sigma k, and this is 1 over k factorial sigma in Sk sine sigma. Now here alpha of V sigma 1 etc. V sigma k, since I have assumed that alpha is alternating, what I get here is again another sine sigma and then alpha acting on V1 up to Vk. So I can take out this alpha acting on V1 up to Vk, then I have a k factorial here. I am left with sigma in Sk. Now the sine sigma, whether it's -1 or +1, we have a square here, so I'll just get 1. So I'm summing, and this sum contains as many terms as there are sigma in Sk, which is exactly k factorial terms. So the number of elements in Sk is k factorial. That k factorial cancels with this k factorial, and I'm left with alpha V1 up to Vk. So that proves the two properties of alt that I wanted, and as I said, it's easy to check as usual. The map itself, the alt map, it's easy to check that alt from LKV to AKV is linear. So alt of the sum of two forms is the sum of their alts, and as similarly alt of a constant times a form is constant times alt of that form. So I won't write it down. These are fairly straightforward. Now what I want to do is, just like we had a nice basis for LKV, if we start with starting with a basis for one forms and the tensor product, we could get a nice basis for LKV. Similarly, I would like to get a basis for AKV starting with one forms. However, tensor products will not do the job. So tensor product of two one forms, for example, is not an alternating two form, just a two tensor. So one would like to combine one forms in a somewhat different way and get a basis for AKV, and that's where this process of alt is going to come in handy. So this, now we come to this important operation of the exterior product. So in the world of alternating tensors, this serves the same role as the tensor product. We would, in other words, we can combine a K form, alternating K form, and an alternating P form, and get an alternating P plus K form, etc. So, and the way I define it is, I actually end up using the tensor product, but I have to do something more. So the exterior product is a map from, as I said, AKV, the input is 2 ARV, and I'm going to get something in AK plus RV. So omega eta, and this will be denoted by omega wedge eta. This is also called wedge product. And if I start with omega and eta, well, I can forget that they're alternating, just think of them as multilinear forms and take the tensor product. Then I'll get a K plus R form. But then, now that I know that given any multilinear form I can get something alternating out of it, we can apply alt. So that is essentially the idea. So let's define the wedge product omega in AKV, eta in ARV. So let this omega wedge eta I define to be, for the moment I'm going to ignore constants. The constants actually play an important role here up to a constant. So it is essentially alt of omega tensor eta. If one wants to spell it out, so one can see what its action is on. So this is going to act on V1. So I will give different symbols for the variables, V1 up to Vk, and then W1 up to WR. So altogether there are K plus R input variables, input vectors, and what I'm supposed to do is, well, I'll have to do the alt operation already involves a factorial K plus R factorial, and then sigma, and now this is, I'm going to apply alt to omega tensor eta. Omega tensor eta is a K plus R multilinear form. So I'll have to take S K plus R. And then, now here I'll be doing, I forgot the main thing, which is sine sigma, and then omega tensor eta of V sigma 1. Oh, here actually, sorry. So I have to be consistent with this notation. I cannot really use this separate variable. So let me just go back and call it Vk plus 1 Vr. Then this will be V sigma. So here K plus R, not Vr. V K plus R. And then here it would be sigma K plus R. Right. And one can expand this a bit more. So sigma in Sk plus R sine sigma, and by the definition of the tensor product, I will end up acting omega on V sigma 1 all the way up to V sigma k, the first k of these variables, then multiplied by eta acting on V sigma k plus 1 V sigma k plus R. So this is what it is, the last expression. So this is the definition of the exterior product, if we have simplified it as much as we can in general setting. All right, so now there are lots of important properties of this exterior product. Again, the first thing is that this product is again an alternating form. This is the first observation. That of course is true because I have applied alt, and we have seen that alt takes any multilinear form and makes it alternating. So that is okay. Given that, there's a bunch of important properties of this exterior product that I'll write down in the next lecture. That would be a good place to start. And then I won't be able to prove all of them. So maybe some of them I'll discuss. We'll stop here at this point with the definition of the exterior product. In my next lecture, I'll talk about its the main properties of this. And then the plan is to move on to, all this while we have forgotten about manifolds. Now we'll go back to manifolds after that and sort of carry over all these properties to the setting of manifolds, all these constructions to the setting of manifolds. Okay, thank you.